This is the first lesson on annuities. I will have a second lesson on the same topic. In this lesson, I'm going to talk about some terminology, accumulated value of annuities, discounted value of annuities, and something called annuities due. On this slide and the next, I have a number of definitions. An annuity is a series of payments, usually but not necessarily made at equal intervals of time and in equal amounts. The formulas in this lesson apply to equal interval, equal payment case. The time between successive payments of an annuity is called the payment interval or period. So that's similar to what we were talking about with interest. The time from the beginning of the first payment interval to the end of the last payment interval is referred to as the term of the annuity. When the dates of the first and last payments of an annuity are fixed, the annuity is called an annuity certain. When the term of the annuity depends on some certain event, for example, someone passing away, the annuity is called a contingent annuity. It doesn't have to be death. It could be retiring from work, going on Social Security, birth of a child, something like that. When payment is made at the end of each payment interval, the annuity is called an ordinary annuity or immediate annuity. When payment is made at the beginning of each payment interval, the annuity is called an annuity due. A deferred annuity is an annuity whose first payment does not begin until after a specified deferral period has elapsed. I have a few more definitions on this slide, and I know this could be a bit overwhelming. I'll try to bring up the definitions as I get into the mathematics for the different cases. So that'll hopefully make things a little bit easier. So let's continue. When the payment interval and the interest compounding period are equal, that is, payment and compounding occur at the same frequency, the annuity is called a simple annuity, and we'll be talking about those next. Otherwise, it is a general annuity. For example, a mortgage with monthly payments and monthly compounding is a simple annuity, whereas a mortgage with monthly payments but semi-annual compounding, as is common in Canada, is a general annuity. The accumulated or future value of an annuity is the value of the recurring payments to an annuity at a certain date in the future, assuming a particular rate of return. The discounted or present value of an annuity is the current value of future payments of an annuity given a specified rate of return or discount rate. So we've already seen some concept related to discounting, and we'll apply it again to annuities. The higher the discount rate, the lower the present value of the annuity. Our first case, we're going to look at ordinary, simple, certain annuities. And just to remind you, out of all our definitions, I have them down here again at the bottom, at least the three that pertain to this. When payment is made at the end of each payment interval, the annuity is called ordinary. You can see here we're making a payment of R at the end of interval 1, 2, 3, up to N. When the payment interval and the interest compounding are equal, that is, payments and compounding occur at the same frequency, the annuity is called a simple annuity. So we're going to make a payment here, and of course nothing has been paid yet, so there'll be no interest here, but then at the end of the interval 1, we'll have compounding on this initial payment, and then we'll add another R, whatever, dollars, whatever currency. Then when you get here, you would do another compounding based on this amount of what these two are worth at that point, and so forth. And then it's also an annuity certain because it starts at a particular time, and then it goes on for N periods, which could be months, could be quarters, could be years, whatever, but it's certain. So the amount of R is deposited at the end of this period here, first period, and then at the end of the second, third, and all the way up to end. So there's end payments with interest being compounded at each one of the same time as each one of these payments. And on the next slide in the figure, actually the table on the next slide, I'll show you how to add all these up to find out how much money you have at the end after you've contributed all this money. So this could be, for example, maybe you're saving for a child to go to college and you started 10 years before their anticipated start date of college, and so you're putting in money maybe every month over those 10 years, and you're accumulating interest. So the interest accumulated on this very first payment is going to be the most because it's been in there for the whole period, and then this is like 1 month less, one month less, and so forth. And then the last payment, of course, you put the money in there, but there's the annuity is done at that point, and you would make no interest on this last payment. And then you would have a pot of money to pay for your child's college tuition, for example. Okay, so let's look at the computations on the next slide. On this slide, I want to compute the total value of the annuity at term. No interest is earned on the contribution at the end of period end, since that is the end of the annuity's term. So that's this here. Then the amount of interest, or the value of this deposited here at the end of term, is R, and then the interest accrued, I times R. So this payment is worth R times 1 plus I at the end of term. And then the payment, which I don't have here, but the one just before it, that accumulates interest over 2 periods. So just using the compound interest formula, that would equal R times 1 plus I squared. And you go all the way back to this one here, and this accumulates for n minus 1 periods. So its value would be R times 1 plus I to the n minus 1 power. Then we want to sum all these up. We can use the formula here for the sum of a finite geometric series. We have A equals R, capital R. Small r here would be 1 plus I. And then this is up to sum to n, but we're just summing to n minus 1. So we would have n here in our formula. So we plug things in, R, capital R for A. Then we have 1 minus 1 plus I to the n. Then 1 minus 1 plus I. So on the bottom, on the denominator, we get a minus I. And up top, we get this here. And I just brought the minus 1 up here, so I shifted the order. So this is the value of the annuity at term. Sometimes this quantity here is given a notation. It'll look like this, Sn slash I. Sometimes you'll see it as S and comma I. There's different variations. I just pointed out here in case you're reading different books or material related to annuities, you may see this notation. Let's look at a few examples. Mr. LeBeg agrees to an annuity savings plan from an investment company. Under the plan, Mr. LeBeg will contribute $300 at the end of each month for a period of 3 years. Interest is compounded at the end of each month at a nominal annual rate of 6%. How much is the annuity worth at term? So we have R equals 300, N equals 3 being number of years, 12, given he's paying into it once a month. So you get 36 periods. Then the rate per period would be 0.06 divided by 12, or 0.005. And then we just plug into our formula from the previous slide. So we have R is 300, 1 plus I is 1.005 raised to the 36th power minus 1 divided by I, or 0.005, and we get 11,883 cents. Then let's say Mr. LeBay reconsiders and tells the investment company that he really needs about $15,000 to buy a car in 3 years, and would like to know how much he needs to save each month to reach that goal under the same conditions. So now we're given S, in other words, the final result, which is more than the 11,000, it's 15,000, and we're looking for R. So we just take this part here and multiply it on both sides by the reciprocal. In other words, multiply by I divided by 1 plus I to the n minus 1 on both sides, and that isolates R. And then we just plug in the values we have here. I is, as before, 0.005. S is 15,000. Then we have I plus 1 to the 36th power minus 1. And so he would need a little bit more, actually quite a bit more. He would need $381.33 every month under these interest rate conditions to get to his goal of $15,000 over a 3-year period. And yet another variation of the problem, assume Mr. LeBay wants to limit his monthly payment to $300, but is willing to wait longer to reach his goal of $15,000. So we want to look in, for this case, we want to find N. We want to know what N needs to be in order for him to get to this amount. So this is an algebra problem. I've kind of left a few steps out, but I can talk through them here. We first multiply by I over R on both sides. And then we add 1 to both sides, and we get this here. And then we take the natural log, in other words, a log base E, where E is Euler's number, on both sides. And that gives us, on this side here, it gives us the log of 1 plus I times N. We can just divide that into this side here, which we've taken the log of, the natural log of, and we get this equation. So for the problem at hand, we get N equals 44.74. So we would want to round that up, and the message to Mr. LeBay would be that if you want to actually not go beyond your 300, but still get 15,000, you would need to extend the annuity. Instead of 3 years, you would need 45 months basically to make your 15,000. Unlike solving for S, R, or N, there is no closed form algebraic solution for the interest rate. And you can see that here. If you take our initial formula for annuities, multiply both sides by I, you get this here. You can write it out a little bit more. And if you multiply this out using the binomial formula, you basically get a polynomial of degree n with the variable I. And for n greater than 4, there is no general algebraic formula for the roots. So I cannot be isolated symbolically. You need to use a numerical technique to find I. So this has some practical value. Going back to the problem from Mr. LeBay, he has yet another option. He could look for a variable rate annuity that would still allow him to put in the $300 per month and end up with 15,000. And that might be advertised as variable rate annuity. In the past 5 years, the interest rate is average 7%, but this fluctuates based on market conditions. So he's kind of taking a chance. It could be, considerably less than the 7% over the period that he's investing, or it could be more than that. So that would give you cause to kind of look for solving I in this equation where you know everything else. In other words, he's kind of set on 15,000 at the end and doing 300 a month, and even the length of the annuity, and he'd like to take a risk with a variable rate annuity, which I don't talk about much in this set of lessons, but I'll mention it here at least once. I misspoke on the last slide. I actually do talk a little bit about variable rate annuities. What threw me off is the term blocking is used here. You'll see what I mean in a second. So especially for longer term annuities, the entity offering the annuity is not likely to provide a fixed interest rate for the entire term of the annuity. The investment entity may vary the rate based on something like the 30-year United States bond interest rate or long-term bond in another country, same idea. In such cases, the computation of the annuity's value needs to be blocked into several computations. So you're going to compute the annuity each time, or recompute the annuity each time the interest rate changes. And those are the blocks. That's why it's called blocking. So I have an example here. We have a Ms. Gold agrees to an annuity savings plan from a bank that stipulates a deposit of $500 at the end of each month for 10 years. The interest rate is based on the 30-year Treasury bond rate for the past month, whatever country she's in, for example. For the first 5 years, 60 deposits, the nominal annual rate remained constant at 3% compounded monthly, and for the last 5 years it remained constant at 3.5% compounded monthly. How much was the annuity worth at term, assuming Ms. Gold had contributed the agreed $500 per month? So I'll give you the answer on the next slide, but you may want to try it. It's basically two annuities, computing two annuities. One for when you have the 3% and one when you have the 3.5. And we have the formulas for that. So it's just a matter of breaking the problem into two pieces. There are basically three parts to this problem. We first compute the value of the annuity at the end of 5 years. So we have our formula for annuities. 500 is the monthly deposit. Then the monthly interest rate is 0.03 divided by 12. Then we have here this number of periods is 60, and we get this number here. Then we compute the annuity over the second 5 years. So everything's the same except the interest rate is a little bit higher. So we get the 0.035 divided by 12 here and here. And we get 32,733 and 6 cents. The piece that's missing is this S1 continues to accrue money over the second 5 years. So we have to do compound interest computation on this, and we know that formula. So this is our initial principal. Then the rate is 0.035 divided by 12, and then over the next 60 months, you're not depositing $500 anymore related to this. You're just accumulating interest. So the total value of the annuity at term is this here plus this. So it's $71,228.33 cents. While Ms. Gold contributed a total of 120 deposits of $500 or $60,000. In a variation of the above problem, assume the term is changed to 15 years, with the first 10 years being as before, but the last 5 years the nominal rate is 6% compounded monthly. Further, Ms. Gold does not make further contributions beyond the first 10 years. So the money is just being held for another 5 years before she starts cashing in, but it's still earning interest. So without even adding any money, just working off of interest, you again use the simple compound interest formula on our $71,228.33 cents, and it grows to $96,076.34. we can make blocking more general than what we saw from the previous example. Each block could have a different interest rate per period, a different payment amount per period, and a different number of periods. So each block is identified by three variables: interest rate, payment amount, and the number of periods. And whenever you change either one of these two, interest rate or payment, that kind of demarks the end of a period. So really these two attributes, interest rate and payment amount, determine the third variable, the number of periods in a block. So how do we compute this? Well, we already have the basic formula for doing the computation in a given block. So let's say we have n blocks, as we defined up here. So for each of the n blocks, compute the accrued value of the annuity for the interval when the block is active. So in other words, during that block, compute the accrued value. This is done using the formula below for block K. The subscript K is put on I, R, and N to emphasize that these values can change for each block. So I put the little subscript, as you notice here, as well as here. So, but this is basically our simple annuity formula. But that's not the whole picture, because if you compute this for this accrued amount for, say, the very first block, then it's, even though you're not adding to that anymore under that particular block, it's still accruing interest, just the way we saw with the 2 5-year periods. That first 5-year period in the example continued to accrue interest during the second period, where you had a different interest rate. So we need to compute that. So for each S sub k, the value continues to accrue during subsequent blocks, not previous blocks, but subsequent blocks, based on the interest rate and number of periods for each subsequent block. So the value at the end of the annuity for block K is given by this formula here. So it's your amount here, and then the accrued interest over the next block, K plus 1, then the accrued interest over this block here, all the way up to the nth block. So this would give you the value of the total value of the money accrued during the kth block, but computed across all the subsequent blocks. And then you need to add all these together. And then this line, this point number 3, is more of a note. The very last block, you don't need to do this because there's no accrual period after you finish the last block. So the total value of the annuity is just the sum of these V sub K's plus the last one, which we could call V sub M, but it's equal to S sub M. So up until now, we've been looking at annuities from the point of view where you put payments in over a period of time, and then you accumulate a particular amount of money at term. There's also going in the opposite direction. You'll see this sometimes when people retire and they have a pot of money, or at least part of what they've saved, and they want to have a steady income coming every month. And so they would purchase an annuity up front for a given amount of money, and then it accumulates interest while the money's in there. But at the same time, there's a payment to the purchaser of the annuity every month. Eventually it runs out, but the idea is that it could be used as a sort of a retirement fund. So that's what we're going to look at here. It's called discounted present value of ordinary simple certain annuities. So consider a scenario in which someone purchases an annuity up front, as I explained, and then gets constant payments in the amount R at the end of each of n periods. At the end of period n, the value of the annuity is 0. The interest rate per period is I. So you continue to make money while there's still money left in the annuity. In order to cover the first payment, end of period 1, how much needs to be invested at the beginning of period 1? If we call this quantity x1, then we need to solve this equation here. X1 plus x1 times I, the interest rate, needs to equal R. That's the amount of money we want to get out at the end of the period. So we solve that and we get x1 equals R times 1 plus I to the minus 1 power. So x1 invested at the time 0 will be worth R at the end of the first period. This is basically a present value calculation for a future desired amount, which we've seen these before. So in general, we need to calculate the present value for each of the end payments of amount R and then sum the amounts. So we've done the first one already here. Then the second one would be 2 periods out, so it would be discounted more. That would be R times 1 plus I to the minus 2, and so on. Eventually, you have to discount that last payment, R times 1 plus I to the n minus 1 power. You can factor out an R times 1 plus I to the minus 1. Then this first term is a 1. This is 1 plus I to the minus 1, and so forth, all the way up to the last term, and it's 1 minus that, because we factored out this here. And so this is a geometric series with A equals this first term, or this thing that's multiplied times all the terms. Then R is 1 plus I to the minus 1, and we plug that in to the formula for geometric series, which I showed you before, and we get this equation here. So this is our A, the term here, and you have 1 minus the R to the n power, and then this in the denominator. Okay, so let's look at an example, or some examples of this. Actually, I jumped the gun a little bit. The examples are on the next slide. We have a little bit more computation to do on our results. So Q is the, I've carried this over from the previous slide. Q is the amount you need to invest or buy the annuity with in order to have these R payments for n periods before you deplete all the money, under the assumption of this interest rate per period. So we can do a little bit of simplification, multiplying by 1 plus I divided by 1 plus I. So this is 1. So we multiply that times this here. You notice this term here becomes just 1. Then in the denominator, you get 1 plus I, and then this is 1. So you get 1 plus I minus 1, you get I. So you get a sort of a, I guess, a little bit more pleasing looking, simpler, slightly simpler solution here. So we'll use this. That's why I put it in bold. So, and just to summarize, so an initial investment in the amount of Q with interest rate I per period, compounded at the end of each period, is equivalent to n payments in the amount R at the beginning of each period. And as I say, when you get to the last period, at the end of that, you've depleted all the money in your annuity. Alternatively, the above formula can be solved for R in terms of the other variables. It's pretty easy. You just take the reciprocal of this and multiply times Q. And so you can, given Q, I, and N, you can figure out, well, in other words, if you had so much money to invest and you knew what the interest rate was and you knew you wanted to have it over 20 years, this formula would tell you how much you would get per month, which is what I described here. And then we can also solve for N to determine how long an initial investment will last, given the distribution amount per period and the interest rate. So if you solve this for N, it takes a bit of work. I'm not going to do the algebra. You may want to try it if you need an exercise, but it involves taking the natural log on both sides and then solving for N, and you'll get this solution here. So Ln is the natural log base E, where E is Euler's number. And then I have a remark here. This quantity, which appears here, is often represented by a shorthand notation in financial books and articles. And you'll see something like A sub N bar I. Sometimes you'll see a comma. Just to let you know that you may see something like Q equals R times this expression here. Okay, now for some examples. What initial investment is needed to get a monthly payment of $750 for 20 years, given a nominal yearly interest rate of 5%? So this is an annuity that somebody might want to buy in retirement, and maybe they're not quite ready to purchase this, but this is sort of what they're thinking they need to supplement their income. So they want to know what's their how much money they need to save to buy that annuity. So we're given R, we're given N, it's compounded monthly, 12 times 20, 240. And then the interest rate per period would be this, 0.05 divided by 12. We have our formula from the previous slide. We just plug in all the numbers and we see that you would need $113,643.98, and that would give you $750 over 20 years, and your annuity would be depleted at the end of those 20 years. As a second example, consider someone who has $100,000 to invest in an annuity with a nominal interest rate of 4% compounded monthly, and wants to have the annuity distribution distributed monthly for 15 years. How much can be distributed each month in the given period, in each period? So in this scenario, we're given Q, N, it's 180 this time, and I. And so now we use the second formula we had on the last slide, which I've written here. And we plug everything in, and that person could get $739.69 every month for 15 years under these conditions. We have one more example on this topic. We want to find the number of quarters that an investment in the amount shown here will last, given equal quarterly payments of $1,000 and quarterly interest rate of 0.013. I didn't bother giving you the annual rate and dividing by 4. I just gave you the quarterly rate directly. So we have R is 1,000. Q is this 27,000, almost 28,000. And then I is 0.013. And we want to find N. And we've solved that equation earlier, so I've written it down here again. We just need to plug things in, and we get 35. So the annuity can pay out $1,000 per quarter for 35 quarters, or 8 years and 9 months. In most cases, the N is not going to be a whole number. In fact, I'm not sure I may have rounded this off. So in such cases, the final payment will be less than in this case, the $1,000. There might be a little bit left over. In an annuity due, the periodic payments are due at the beginning of each payment interval. If you recall, the very first annuity we talked about, the ordinary simple annuity, we had the payments at the end of each interval. So this is a slight variation from that, and let me point to it. I have the diagram here. So we have the first payment at time 0, and then 1 at time 2, and so forth. And then at time n, there's no payment. So the accumulated or future value of an annuity due at term is similar to the formula for S, again from our very first example of annuities at the beginning of this lesson, except that the interest is earned on each contribution for one additional period. So we need to multiply the formula for the accumulated value of an ordinary, simple, certain annuity by 1 plus I to get the accumulated value of the annuity due. So that's this here, or if you multiply through, you get this equation here. Okay, so that's just a variation. Then I have one more slide in this lesson. Let's get to that. When we did the computation for the discounted present value a few slides back, the payments from our lump sum that we paid for the annuity up front were made at the end of each period, and we had to discount those to compute the present value. So here there's a slight difference. The payments are at the beginning of each period. So you have R being paid out, and then R times 1 plus I to the minus 1, corresponding to the second payout, and a discount corresponding to the second payout, and so on. And so you, instead of going up to minus n, you go up to minus n minus 1. You can factor the R out of this, and then you just get a geometric series. We use our formula for the sum of a finite geometric series, and we get this here. Okay, so you'll see this in various formulas, whether you do something, pay out, or get paid at the beginning of an interval or at the end of the interval, and typically it's a slight variation of the formula as we've seen here. Okay, so this is the last slide in this lesson, but I have several more concepts to talk about in terms of annuities. So we'll have an annuities part 2, and then I have several programs that I wrote to support some of the calculations here. They're written in Python, and I think I may just do a third lecture where I just kind of give you a high-level view of how to use the graphical user interface for those programs, and then I'll also make the programs available on GitHub, so if you want to use them, you can download them freely.